Hello, and welcome back. This is a continuation of the previous video to finish explaining the communications model. For communications, I really have more to say about the design philosophy than the actual uses, as they are really just for a file system at the moment. But the communication system was designed to be fairly generic and a spin-off of the observer pattern. One problem that I have with the observer pattern is the claim of decoupling code from unrelated systems, which is true, it does this, but then in most implementations I can find, the class or structure itself has to inherit from an actual observer interface, which now couples the class to the messaging system, which isn't too big of a problem, but as I showed previously with the read-write function signatures, I prefer to have room for variable use cases since rarely in software is there ever a truly one-size-fits-all solution. Because of this, I found it better for the messaging and communications to occur on an observer that are not an inheritable interface, but actual concrete objects. On the side of design philosophy, I started with a very hand-wavy rule which states a message must be consumed only by the system which is logically responsible for that message type. Like I said, it's very hand-wavy, but always CYA. Just like with the RCU, I find it helps to be able to visualize the relationship between the data and its states, so I will go ahead and do that now. So starting with messages, messages are a container around a type erased piece of content. Messages also contain a token which is a predefined description about this content. These tokens will be used later to notify the proper observer about the message. To save space, I omitted a few functions from some of the structures, and one of them being the getContentMessage function here. This is responsible for pulling the message content out of the message itself and giving it to the processor of the message. It is important to note that if there are any dynamic allocations which happen inside of the content which is passed to the observer, then that content or those dynamic allocations need to be handled during the processing. Messages are created by passing some token that describes the message and a piece of content that reflects the actual instance of this message. The content is then wrapped around a content wrapper which performs the type eraser. After messages are events, and events are pretty well described in this comment here. An event is essentially a collection of actions which are translated into messages for processing. Event actions are predefined functions describing the potential actions which may occur inside of an event system and provides the translation mechanism from action into message. An event system is the collection of these functions and the descriptions that go along with them into a single logical namespace. There are no differences in underlying type between, say, a file system event and a graphic system event. Because of this, I find it preferable in practice to use typedefs or using statements to define concrete instances of event system types, and I will show this a bit later in the code. Moving on from events and event systems are event spaces. Event spaces are essentially hubs for routing event messages to the observers of the event space. Here, that very hand-wavy rule comes into play. Using the rule that each event type or message must be processed by one and only one observer, then very clear lines of communications become apparent. Every bit of data is predetermined even before compilation. I went with this design choice for two reasons. The first was my dislike for how the observer pattern traditionally couples the observing class with the interface itself. The second is cross-thread communication, which is the big one. Now, with either this or the traditional pattern, both ultimately look the same in runtime if you actually trace out the data, but the traditional pattern allows for multiple paths for one piece of data. However, that also means that cross-thread handling of the data and cleanup must be done very carefully. If only a single observer is used to access a given type of data, then the event space itself can handle the synchronization of message passing, and the actual processing and cleanup of the messages are able to be done freely by each subsystem observer. And now we can finish off with the observers themselves and their register. The registration is simple. It just stores pointers to the observers which are registered to their event spaces during the initialization phase. There is also a check done in the registration process to make sure that two observers haven't been registered to the same token. The observer themselves have their own token where each bit reflects um, which message type they're able to observe. This provides for up to 64 message types per event system which may be observed. Observers also use an exchange lock, which under the hood is really just a spin lock, but I call it exchange since that's what the instruction is that's used to spin. The exchange lock is used by the event space to make sure that if two threads are attempting to push events through the event space, only one thread may notify the observer at a time. The observer will also take the lock themselves when grabbing observed messages during the process events function call. All in all, though, that is the entirety of the communications model, and I'll go over the actual interaction and implementation of a couple systems that are currently in use now. So this is the file system that is implemented using the communication system. It contains a collection of message types that describe the data that it can encounter when processing a file, and currently only a single function to load a manifest binary database file. However, it should be clear shortly at least how this would be easily extendable to other file types in a file system as they come along, such as terrain files. The idea is that somewhere in the code, something will trigger an action. For example, this test scene function here, which invokes the file system load mbd function. This function will import the binary database and create a message containing a token that reflects the type of data that was loaded from the file, as well as a copy of the data itself. One side note, this function is still using the scratchpad allocator, so the memory could technically be lost should the allocator be reset and used again while the messages are in flight or being processed. But for testing purposes, this is fine, and as stated in previous videos, there will eventually be a more permanent allocator for objects with variable lifetime. After each action in the event has been translated into a message, the event is broadcast to the observers registered to the event space, which was passed in to the event action. The event space calls its notify function, which searches for the observers responsible for each message. Once the observer is found, its observed message function is invoked, and the message is passed to the observer. Now, in the future, it might be better to set up a list of messages per observer as they are found, and then pass these completed lists to each observer, since the spin lock has to be locked and unlocked each time observe event is called. However, after this, the messages will stay in a queue for the observer to process once invoked by the subsystem in which this observer is working for. Taking a look at the physics engine first, it has one observer who is interested in only geometry nodes from the database files. When the simulation is updated, the physics engine will check for pending messages, and if detected, will process them accordingly. Since we only have the one observer, in this case it's very simple. The actual processing from this point forward, though, is more specific to the subsystem itself and the type of observed event. Now, what I want to point out here is what seems like a sidestepping of the rule. Rather, this is the rule working as intended. When originally writing this code, I was wondering how exactly the physics engine would link state to specific objects for the graphic system. And when I took another look at the rule, I realized that it's the physics engine who is interested when new object nodes are created from a file system event. This is because the node will ultimately be primarily handled by simulation. The graphics system still needs to know about the node and how to link the data to it, but graphics is only interested in the fact that the simulation is creating a new object, not the fact that there is an object loaded from the file system. And this is because, as I'll show in a moment, the graphics system is responsible for handling the visual resources as well as displaying the generated simulation data. Therefore, it is actually the physics engine itself who is responsible for notifying the graphics of a new object and not the file system. You can also think of situations in which objects are procedurally created in the simulation, and this allows the same communication channel to be used to notify the graphics engine. And as a side note here, the physics engine's file observer doesn't actually have to be responsible for triggering the action. The signature for a message processing function allows for a pointer to be returned to also signal further messages to be created. Since this is such a trivial case, I have the observer trigger the action in the process function. Taking a look at the graphic side of things, we see a similar situation going on here. On each update, if there's a new message, we process it. And looking at the two observers of the graphic system, there is one for the files and one for the graphics itself. And these are the types which they're interested in. As with the physics engine, the actual details from this point forward are dependent on the processing function. But hopefully this demonstrates the rhyme and reason for why the communication model is the way it is. With all that, though, that is it. Thank you all for your time. I hope you have a great rest of whenever you're watching this, and I will see you in the next one.